of the types of machine learning model stores that exist out there. We focused on Hugging Face, but just to let people know, there are other machine learning model stores. So what is a machine learning model store? Well, a machine learning model store, at least in the context of Hugging Face, is a repository, or it's a series of repositories that has pre-processed machine learning data sets and pre-trained machine learning models. And for our use case, we focus on Hugging Face, basically because Hugging Face is originally valued, or was originally valued at $80 million. It's also a growing important tool in the machine learning community. Then it also provides certain advantages such as version controlling, such as Git. And it also uses documentation standards that are backed by published research. So to go further into what we did, this is like our first RQ, which is what kind of information is documented for the models at Hugging Face. And unfortunately, the answer is not much. So you have like 60.38% out of 55,280 models at Hugging Face. These are not documented. So if you are going to use a model with Hugging Face, it's far more likely that whatever you're going to use is going to end up being an empty page. That's not great. But anyway, to further look into the documentation practices of Hugging Face, we also looked into the models that are actually documented. And what we found is that out of the sections that are present in the standards that we used, or the published standards that we mentioned, well, there are 7 out of 9 out of those sections, but the most important ones are model details, training data, intended use, and evaluation data. Then you have some other stuff like metrics, and of course caveats and recommendations and ethical considerations are pretty much non-existent from what we found. I'm pretty sure that there was 1 or 2 appearances of these sections. So when it comes to ethical standards, those are not very important for the documentation of models. Then we also performed a manual analysis on these model cards to sort of classify how they follow these standards as well, to figure out if a section was truly reflective of the 9 sections that we had or not. And basically they were matched on whether they had content, or they had content mismatch, or they had no content. And once again, ethical considerations and caveats and recommendations are not documented. Okay, so now we move on into the data sets. And we also check for what kind of information was present in the data sets in Hugging Face. And once again, the result is not great. In this case, it's 71.52% of all the data sets that are not documented. So once again, if you're going to use a data set on Hugging Face, it's very likely that you will run into an empty page with no documentation. Then we also did some manual analysis based on the sections that are present for Hugging Face, which are these 5 sections, which is dataset description, dataset structure, dataset creation, considerations for using the data, and additional information. And what we find here again is that dataset creation and considerations are mostly undocumented. So why is that important? Well, these are the ethically related sections once again. So when it comes to data sets, people don't care about that and they don't document it at all. And then we did another analysis which was more grounded. So each subsection, or each section has a series of subsections. these results are kind of similar to what we saw before. They're just like a breakdown of what we found per subsection. And it's pretty much like the same answer, like the subsections that belong to considerations and dataset creation are once again non-existent or not documented at all. And yeah. So now we move on into what I think most people are going to have questions about, which is how well are dependencies between datasets documented? And the answer to that is that they are not. So for our analysis, we extracted a series of datasets. This amounted to 2.0 or 2 terabytes of data. But anyway, out of the datasets that we actually found that had any references, like only 20 of those, 9%, made any reference to any other dataset. And this does not mean that they were dependencies or that there is some sort of connection to these datasets, but that when it comes to the documentation, there is a reference to one dataset from part of another. And we'll go further into this. So besides checking for what's documented or not, we also have to identify like how these datasets may have been similar or not. So we use a tool called SD hash, and with that, we produce this histogram here, which talks about the average similarity scores. So we took all the datasets and then we ran SD hash to find similarities between these datasets, and what we get is this like score distribution. And perhaps the most interesting part about it is that there are a lot of outliers. Everything that lies beyond the 60 threshold is sort of an outlier. And this is what can be defined as a clear set of data sets with disproportionate similarity score and a significant amount of connections. That definition is important. It will come up again in the next slide. Yeah. So as part of our result, we found that there are 28 data sets that represent the cores or the important data sets of the 214 merged dataset nodes that we retrieved. So once again, I would like to bring up that definition. So there is a clear set of data sets with a disproportionate similarity score and a significant amount of connections within the graph. So like before I mentioned these 28 data sets, well, that definition fits into these data sets. So when I say that there is a clear set of data sets with a disproportionate similarity score, once again, these are those 28 data sets. And this can be defined as a core periphery structure, which can be visualized in this way. So what we have here, this center is your 28 data sets, which are what you could say are the most important data sets. These are your cores, and then everything that surrounds these cores is a periphery. So you have purple, orange, teal. Those are peripheries. These are also data sets, but they are data sets that are not as important as these core data sets. And the important part about all of this is that, well, we found that there is a very strong similarity between these data sets. I can't say if they are dependent or not. That's difficult to know. But if they are, then they're not very well documented. Like I would like to remind everyone again that only 20 of these data sets had any mention to any other data set. And they never really specified if they were like dependency or not. So yeah, in conclusion, Hugging Face is a microcosm of the problems that exist in machine learning, such as, issues with dependencies, problems with ethical standards, and so on. And well, this little image is what a microcosm looks like. That's like a small world. So you could say that Hugging Face is like a small world of machine learning's problems. And finish up, well, I remind everyone what we saw about models, then what we saw on data sets, and finally, what we saw about dataset dependencies. And that is what documentation practices of third-party models and datasets is about. Thank you very much.
All right, thank you so much, Ernesto. That was short and sweet, but jam-packed with lots of interesting information. So now I'd like to ask if anyone has any questions for Ernesto about his research. Please go ahead and take yourself off mute and ask your question. Jasmine, I see you've raised your hand, so please go ahead.
Yes, hi, Ernesto. Thank you for your very interesting presentation. So I was just wondering regarding the data set dependencies, right? It's kind of reminded me of the data dependencies that we have this issue in machine learning. And I was wondering if you had any idea for future work in this direction to detect more of those data set dependencies and how it could be implemented and integrated into the Hugging Face ecosystem.
Well, it's kind of difficult to know, like to actually propose something right now. I think like that's that could be like an entire new project. But like what we did here is sort of an approximation. So we use this tool SD-hash, and then it like sort of detected some things. That tool is not made for, you know, detecting dependencies. But I guess if someone wanted to do something like that, I guess they would have to create something similar to dependency resolvers that we see in software. But then you also need like you would also need to know like where the data came from, because some data sets sometimes they inherited data from other data sets, and sometimes that's like documented, sometimes it isn't. But yeah, like of course there's like a huge opportunity in future work, like whoever figures out how to, you know, like create a data set dependency resolver, well, you're probably gonna make a lot of money or something. But yeah, that's what I could say anyway.
Thank you.
Okay, thank you, Jasmine. Divya.
Hi, Ernesto. I just wanted to ask a small question. You notice so many of these data sets and models are not documented, but are they used more frequently or less frequently than the ones that are properly documented?
Well, I didn't look into whether they were used or not. Sometimes they did have a disproportionate amount of downloads, but this was like an odd outlier for the ones that weren't documented. So like Hugging Face records how many downloads a data set or I think it's a model, yeah, how many downloads a model has per month. And sometimes one of those, some of those not documented models were used a lot. I don't know how, because I mean, there's no information on how to use them, but apparently somebody was using them. So yeah.
Just recently, I was using Hugging Face for one of my projects, and I noticed that one of these models were not documented. But the procedure that I had to use to download these models were either written in the using in transformers section, like the code which shows how to use the model from where you import the model, or they were pretty similar to other model cards which were properly documented. So I just wanted to know, like, if not having documentation was actually affecting the usage.
Well, you could say it is important for other reasons. Like, for example, there's a particular case with a model that Google did a long time ago for the NHS, the National Healthcare System in the UK. So they didn't document a lot of their things. And some of those things were related to ethical concerns. And when they didn't do this, well, they had an investigation, and then they had to halt the deployment of their model indefinitely. So, I mean, I don't know if anybody's going to use one of these models at Hugging Face in that capacity, but it's something that can happen if you don't document your ethical information, and you can run into these sorts of legal issues. I mean, if Google, if they can catch Google, they can catch you.
Right. Thank you.
Thank you, Divya. Any more questions?
I actually had a similar question to Divya, but I think she asked it pretty well. But in general, I think like my question was like, what are the implications of these bad documentation practices? And I think Ernesto, the example you gave at the end is a very strong example, right? So I think trying to motivate the work is like the first thing people think is like, oh, like then these are not usable, right? And so let's say they won't have a lot of downloads or usages or whatever the metric is for them. But I guess like kind of emphasizing that there are other repercussions is a very good way to go around that. And just kind of as another question, so do you have ideas of how you want to improve the documentation? I don't know if that goes within your scope of like your research or if it's just investigating the practices, but any ideas for how to improve them or tools that would help?
Well, I think there's a qualitative study missing here. Maybe they should just ask the developers and the people who use Hugging Face to explain why they don't document the ethical sections. I mean, seems like that's the easiest way to do that, because apparently, I mean, maybe these standards are very interesting and they've been published or whatever, but they don't seem to be working very well. People don't really follow them, and they just leave out things blank, because even with the cards that are documented, they're like inconsistently documented. Not everything is always full, and like we saw, everything that has to do with ethics and ethical standards, that's like forgotten. So I would say that's like your first way to check into why this isn't being done, and maybe those standards are not efficient enough. I don't know, but I would start there.
Okay, thank you.
Thank you, Dr. Nadi, for your question. I see we're at about 11:20, so we do have a little bit more time to spend on Ernesto's talk. If anyone has any other questions or something that stood out for you that you might be wondering about, or Sharon, please go ahead.
Hi, Ernesto. It was a great talk. I just want to bring up something that I've also noticed is that there's some maybe not data sets on Hugging Face, but really popular ones, like for example, Lion. I'm sure you've heard of it. And even then, they've also, been upfront about how there are biases in their data set because it's unfiltered. They just basically crawled through the web to collect billions of images and text. And they keep advising, oh, this is only for research. Oh, don't use this for commercial usage, but obviously no one's going to listen to that. It's not like it's prohibitive to use it for commercial. They just advise. So it seems that a lot of advisory or even just being straight up upfront about biases or the downsides of your data set is not enough to stop people from using it for potentially applications that will drive ethical issues. So, I mean, I don't know what there is at the moment to really prevent people from misusing such data sets, or even, preventing such data sets from being created. But I think, what do you have to say about, outside of Hugging Face, of course, but even then, these data sets are also going to be used for Hugging Face models, right? So what do you think about that?
Well, right now, there isn't a lot that you can do to stop people from using these things. And I also wouldn't want to say that I want to stop them from using them. I mean, I guess there are regulations. For example, you have GDPR, but I don't really think that's enough if you still see these things going around. So I guess someone probably has to think about more regulation. For example, Hugging Face already has a feature where if a data set has a certain privacy concerns or licenses, you have to agree to the terms of use of that data set, and you have to leave your contact information. I don't really feel like that's enough. And there are use cases. There is a very famous data set that's called book corpus. This was one of the papers cited on my research. Well, there's a lot of data sets that derive from that data set, and they all carry the same issues with biases and problems of that sort. So it's kind of difficult. Like maybe they could establish some sort of regulation, like if you're going to use these data sets, they have to follow this and that stipulation, but that's like difficult for me to say. I feel like that's more of a problem for a lawyer to solve. But yeah, basically like right now it's like the Wild West.
Yeah, exactly. I also feel that way. It seems like, well, I guess we see that every day in the news, like all of these concerns that are really popping up nowadays. And it's really just like laws and regulations that are really behind. And that's like that's the thing that will prevent people from misusing it the most, is when there are legal issues. So yeah, thank you for sharing.
Great question. Thank you, Sharon. I think we have time for maybe one more question for Ernesto, if anyone has one. No, I don't see any hands raised. No more questions? Okay, well, in that case, thank you very much, Ernesto, for your talk. That was very interesting. And good luck to you. I understand you're finishing up your master's.
Yes.
So I think you're our very first CREATE student to complete our program. So congratulations to you, and thank you for all of your hard work over the past year and a bit.
Yeah, thank you very much.
All right, so with that, I think we'd like to move on to our second speaker, Rached.
Okay, I'll share my screen.
You can go ahead, thank you.
Okay, so you can see my screen, okay? You can see my screen?
Yes, yeah,
Okay.
we can see it, thank you.
Okay. So hello everyone. I'm Rached, and yeah, I'll be presenting my the study I'm doing right now. It's called it's a debugger for deep reinforcement learning. So it's called the DRL debugger. It's a tool for debugging deep reinforcement learning frameworks. And here you can see the researchers working on it. So for this presentation, I'll present the following sections. I will start with the background, then the context angle. Then I will explain how we are identifying DRL bugs, how we'll be detecting also DRL bugs, and I will finish with the conclusion. So the first thing is the background. And as you see here, we're focusing on reinforcement learning. I know reinforcement, there's a hype on reinforcement learning, so maybe most of you knows what is reinforcement learning, but I will give a very quick definition of what is reinforcement learning. So reinforcement learning is the third branch of machine learning. We have supervised, unsupervised, and reinforcement learning, and it have a different architecture. So basically, it's composed of an agent and an environment. The agents will be living in the environment, and they will be interacting through actions. So the agent every time will take actions in the environment, and in return, the environment will put the agent in a new state, and it will give it a reward according to the action he takes and the state he's on. A very quick example, for example, Pac-Man. So Pac-Man can be like played through reinforcement learning, and here we can see that, for example, Pac-Man is the agent, and he will learn how to move in the environment, which is the maze of the game. So the action he can take is to move either left or right, up or down. And of course, in return, what the environment will give is a new state. We'll put the Pac-Man in a new position, and it will give it a reward. For example, if he takes one of the dots in the maze, he will get +1. Or if he touches the ghost, for example, he will take -1. And the goal is to try to learn how to move in order to accumulate the maximum rewards. So in the early versions of reinforcement learning, what they did is that the agent to train the agent, they use like simplistic technique, we can say. For example, the pure learning, and the idea was to give a score to each pair of state action. But this worked well when we have small environments, but when the environment was huge, it didn't really work because this problem is called dimensionality clause. And to solve this problem, they introduced the deep reinforcement learning technique. So the idea is that to add to the reinforcement learning, to add deep learning part. So now instead, in addition to reinforcement learning, we have a neural network that will learn how to choose the action it will take according to the states and the word he's at. So deep reinforcement learning consists of merging reinforcement learning and deep reinforcement learning to get more generalistic framework. But what is the context and goal and what we are trying to solve in this study? So first of all, you can see that many industries are adopting deep reinforcement learning techniques. Now there is a lot of research about how to use deep reinforcement techniques, especially, for example, in the robotics domain, they use it a lot because it represents the perfect case of reinforcement learning. A robot has to learn how to behave in any specific environment. But like any other existing software, deep reinforcement learning is at the end a software, so it will have software bugs. But the specificity is that it has a different and unique architectural and behavioral characteristics. We need to define different and specific bugs for the deep reinforcement learning framework, different from the ones that exist for neural networks, for example, or any traditional software framework. So the goal we want to solve first, we want to identify bugs in deep reinforcement learning. By identify, we mean categorize them and develop a taxonomy of bugs that we can find in deep reinforcement learning. And the second thing is we want to develop a framework to dynamically detect bugs in deep reinforcement learning. So now we'll go through each of the points, and I will try to explain the methodology and the preliminary results we have for each one of them. So for the first goal, which is identifying DRL bugs, for the methodology, we follow like classic methodology to collect the bugs we have to collect the bugs. So we started by looking at the literature to see if there is any existing taxonomy for bugs in deep reinforcement learning. We haven't found a lot, so we have also looked at the bugs for deep learning because deep reinforcement learning includes deep learning. And since we haven't found too many, we have added searching in question and answer platforms like Stack Overflow and GitHub to enrich the existing taxonomy. And how we did that, first we have filtered the posts we found in Stack Overflow and GitHub. By filtering, I mean we kept only the post that presents a true bug in reinforcement learning. For example, we eliminated the ones about issues, for example, when in versions of the package or someone asking, for example, what's the difference between reinforcement learning and deep reinforcement learning. When we only kept the ones related to deep reinforcement learning. And of course, then we have labeled the bugs manually. And finally, we have merged the two of them to create our new categories of deep reinforcement learning bugs. Of course, then we have defined those bugs and we have looked at the causes and symptoms of each bugs. Why this is very important for us. First, defining the causes will help us define conceptually the bug because we have to code how we will be detecting this bug. So we need to understand the cause in order to be able to develop the checker or the detector of the bug. And also this is very important because we want to reproduce the bug for the testing. And why reproducing the bug is very important because we want to keep when testing, we want to test on realistic cases. We want to avoid like the artificial bugs that doesn't really happen in the real world. We want to keep them close to reality as much as possible. So the earlier results we have found. So first, for the categories of DRL bugs, we found that there are typically three categories of bugs we can find in deep reinforcement learning. So we have generic programming bugs, which are bugs related to programming, like dividing by zero or the general bugs we can find. Those ones we won't cover, of course, because they are covered in most of the debuggers existing. Then we have the neural network bugs, and those are the bugs related to the deep learning part of the deep reinforcement learning. And finally, we have the reinforcement learning bugs. Of course, those are the ones related to the reinforcement learning part. So first, for the neural network bugs, we have looked on the literature, and our starting point was basically this paper that have introduced bugs in neural networks, which was done also in our lab. And the paper presented the taxonomy of bugs we can find in neural networks, where I will try to give an overview on some of the bugs. Of course, it's an exhaustive list, but of course here I will present the most relevant ones. And I have to mention that the bugs, the way they are presented in the paper, they were for neural networks, but in our case, we have to adapt them to the reinforcement learning. So we needed to redefine many of the bugs or debuggers that were defined in that paper. For example, in reinforcement learning, we don't really have the concept of data or labels and so on. The data are presented differently in reinforcement learning, so we needed to redefine all the bugs related to balance of the data or things like that. So what the paper says is that, as I said, I will be presenting some of the main categories. So they have introduced many bugs. The first group of bugs are starting DNA states. Here we check if there is any issues in the initialization of different parts of the network, like the weight, the bias, and so on. We have issues related to the fitness of a single batch of data. And the goal of this kind of debugging is to see if the neural network will do any kind of overfitting, if there is any regularization issues, and so on. We have the unstable gradients. As the name mentions, we check if the gradient is unstable or not. We have a performance metric correlation. And of course, I have to mention that for each one of them, we have multiple checks that we can do. Of course, you can check the paper for more insight. We have abnormal loss curvature. Here we can see if the loss is decreasing very slowly, or diverging, or it's very highly fluctuating. We have the activation distribution. We want to see if the activations are in the predefined domain, if they have saturated, and so on. We have the magnitude of regularization penalty, and finally we have the parameter states. Parameter states here is basically about, for example, to see if the weights, we have too many zero weights, or we have too many infinity value weights. So we need to do all this kind of checks to see if the deep learning part is working correctly. The second types of bugs in deep reinforcement learning, as I said, are the ones related to the reinforcement learning parts. There's not many papers about that in the literature, but the ones we found is this one. It's called Faults in Deep Reinforcement Learning, and it was among the early papers that defined the taxonomy for bugs in deep reinforcement learning. So again, we will start from the taxonomy defined in that paper, and we will try to improve it with other bugs that we can find in Stack Overflow or Q&A platforms. So the bugs they found basically 4 categories of bugs in deep reinforcement learning, in fact, which are interacting with the environment, exploring the environment, updating the network, and the issues related to the output there. I will go through each one of them. And again, I try to simplify it as much as possible. I want to go through the details of how each one of them is working. So the first group of bugs are the bugs related to the interaction with the environment. And those are typically the errors related when we have issues, for example, with stepping in the environment. And by stepping, we mean that the way the action states and reward are changing are not correlated, and we need to see if they have been like developed correctly, how the environment moves and how the environment responds to the agent actions. We have also issues related to terminating the environment. Typically, we have two subcategories of issues we can find, like missing terminal state and missing the rejected environment. Terminal state is that when the agent starts start learning, there is no final state, so the training doesn't end. And missing a reset environment is issues related when we restart an episode, when we want to start again. Sometimes we miss to do some resetting and to start from the initial state. Of course, all those issues in the paper were found in Stack Overflow and GitHub, and of course those are issues that were reported by developers of the reinforcement learning frameworks. Okay, so the second group of issues are issues related to the exploration in the environment. This is a big problem in deep reinforcement learning, in fact, because most of the behavior of the agent depends on the exploration. And what we have is those issues. So first we have the issues related to missing exploration, not doing the exploration, or issues related to suboptimal exploration rate. And those are generally issues when the exploration and exploitation are not balanced. And exploration is very, very important in deep reinforcement learning. And we need like to evaluate how good was the exploration, of course, because then the exploitation, and when he will start to use the information he got during the exploration, we need to have a lot of insightful exploration. And for example, I can give you an example of issues that happen in the exploration. For example, there is an algorithm called epsilon greedy they use for the exploration, and sometimes people do mistakes when initializing the different parameters they have in this algorithm. Then they have bad exploration, or the exploration doesn't really work, and then the agent won't learn anything during the training. Then we have the updating the network, issues related to updating network. So we have the wrong update rule when you don't update correctly your network. We have the suboptimal network update frequency when, because the frequency of updating the network and changing their weights is not the same in all the DRL framework. Sometimes, many times, in fact, I've seen a lot of people doing this kind of issues in Stack Overflow. Many times people doesn't update correctly the network, which will generate, of course, a lot of issues. Then we have the wrong network update. Wrong network update is because sometimes in deep reinforcement learning, they use multiple networks that can learn different aspects from the environment. And in many cases, people do mistakes when updating the network. They update the wrong network, for example, or the frequency is not right. So this kind of issues happens a lot in deep reinforcement learning. And finally, we have the wrong calculation of gradient. This is typically when you use the gradient of another network to update another network. That happens a lot, of course, in deep reinforcement. The final group of bugs are the output layer. So we have the issues related to wrong output. Typically, the shapes of the output is not correct. It's not like the action shape, for example. And we have issues related to the activation. So we don't have, they use the wrong activation functions for the outputs. Those are those were the kind of bugs introduced in that paper. We have also some new bugs that we haven't yet included them in the taxonomies, but we are still working on adding them and creating new categories for them. I think they are very interesting also to present. So the first, for example, the first bug we have found, the new bug we found, is that many people do mistakes when modeling the environment. But generally in production, or in reality, in fact, people implement their own environment, and they do a lot of mistakes when doing the environment, like how they are connecting to states, like the actions and so on. So we have to do checks to see if the environment was modeled correctly. We have issues related to incompatibility between the agent architecture, the agent deep learning architecture, in fact, and the environment. We have issues related to action that doesn't change during the training. We have also issues related to memories, like observations are improperly stored in memory. So the memory is a part of the framework that stores the data they encounter to use later for training. And finally, we have the undefined action, the action space. This happens a lot when we don't do the right normalization for the action to get an action that is outside of the action space. Now, for the second part of the paper, which was detecting the bugs and how we will be detecting the bugs. First, before going to the detection, I have to mention that I presented the bugs that we have found and the taxonomy of DRL bugs we will be using, but again, I didn't present how we'll be debugging them because this is a bit long. I can't present it for this presentation, but I will give a small example just to explain how we'll be debugging them. But anyway, our DRL debugger works as follows. So this is our DRL debugger. It can be seen as a package you can include in any software you want. We have the checkers. The checkers are the ones that will see if we have a bug or not. So basically, we have the deep learning checkers and we have the reinforcement learning checkers. And for each parameter we will check, will be, for example, for the environment, we'll be doing multiple checks. For the observation, we'll do multiple checks and so on. And we have also the concept of period, because the periodicity of doing the check is different. And we need to make the framework as usable as possible. So the first part of the framework is how to create your own, how to define or configure your own debuggers. So this is, for example, the developer that would use this framework. What he will do is he will define a small configuration file, which is a very simple configuration file. It's an XML file where you just mention the values you want for the different parameters we have. And there is a debugger builder, of course, that will, from this configuration, that will build the different checkers according to the user's configuration. Now, how this framework will be included in the deep reinforcement learning. Of course, we have deep reinforcement learning, and we have the listener that will keep on listening to multiple parameters in the deep reinforcement learning framework, like the observation, the environment, and so on. And then it will go through the checkers to see if there is any bug. And for those who want to know, basically the idea was to redefine the design pattern observer in order to develop this architecture. So the characteristics are basically our typical ones for any debugger. The debugger has to be flexible, it has to be customizable, user-friendly, and easy to use. And of course, we are working a lot on making the architecture respect those characteristics as much as possible. Then for the experiments and evaluation, we haven't started yet the experiments and evaluation, but we will be doing it in like next month, maybe. So for the experiments, first, we are running the debugger on a framework called RLHive. RLHive is a deep reinforcement learning framework that was developed in Mila, and the team that developed this framework are also working with us on this project. And for the next version they will produce, they will include this debugger. So we will be basically working on this framework. For the testing, we are testing on multiple algorithms like DPN, DPO, and for the environment, also we are testing on multiple environments. For the evaluation, we'll be, as I said, we'll be simulating the bugs to see if the debugger would work correctly or not. And also we will be doing some interviews. We are planning to do some interviews to validate the bugs, to evaluate the usability of the debugger, and also to see if we can add any other bugs to our frameworks. Yeah, this is like to finish. This is a very quick example of how we will be debugging. So I took the bug, for example, agent environment and compatibility, which is basically when you don't have there is incompatibility between the deep learning, the agent deep learning network and the environment. So this is an example. The deep reinforcement learning agent should take as input the state and should give as output the action you will take. So the shape of the input should be equivalent to the shape of the states, and the same thing for the output should be equivalent to the actions. And one kind of checks we can do is to see if the input layer's shape is similar to the state shape, and to see also if the actions shape, if the output shape is similar to the actions shape. So this is a simple example of how we'll be doing the debugging. And finally, for the conclusion, debuggers are essential for quality assurance of DRL framework. Also in this study, we have defined DRL bug categories, or we have redefined the DRL bug categories. And finally, we have developed our DRL debugger. And the overall conclusion is that I think that we need to create more domain-specific debuggers in the future that are specific for the architecture or the behavior of the program. So thank you very much, and yeah, I'll be happy to listen to your questions.
Thank you, Rached. Very comprehensive research. Well done. Questions for Rached? Diego, please go ahead.
Hi, Rached. How are you doing? It's a great talk. It's a very interesting concept to think about a debugger in a deep learning architecture and even a deep learning reinforcement architecture. One thing that I didn't quite figure it out, when you think about debuggers, we're thinking about a few characteristics, right? Think about the ability to inspect how things change in a program, like variables change, but also the ability to time travel, to move things, to go back in time or re-execute instructions, things that right now I really have no idea if that's possible in a deep learning architecture. So what are the characteristics of the DRL debugger that today you could map to, like how a debugger works traditionally and how this would work if it would put in practice?
Okay, thank you for the question. I think the main point is that here we will be looking at how the dynamic of the debugger. We want to see if like the rewards they get, or during the training, if the agent is learning correctly or not. Unlike like the traditional debuggers, I've seen a lot of them, because there are some of the people that use debuggers in deep learning, but they are not dynamic. That's why I say this one is more dynamic. They generally generate those. They use the traditional way of debugging. They generate the graphs of the framework, for example, and they start to do some heuristics to check if there is any bug or issues. But in this case, I'm trying to define some rules we'll be following during the training to see if the model is the model's behavior is correct or not.
Right. So more than a debugger, it's a debugger plus a validator of some sorts, right? So
yes,
you have some tests that you kind of execute to make sure like the training is going smoothly in this kind of thing. Is that how it is?
Yes, that's true. For example, if we look at the exploration, which is a big thing in deep reinforcement learning, one thing we can show is that, for example, we'll say that you didn't do a good exploration. It's like to measure kind of the coverage of the exploration, to say the exploration is not quite good. You can improve it, yeah, it's typically to give some warning, to say that try to improve those parts.
Right, and even with maybe some root cause analysis, like okay, what's maybe causing this problem? Is that something you envision could work?
Root causes are a bit difficult to detect, because in many issues, people do some programming mistakes. So those are a bit difficult to explain. But basically, we focus on the symptoms. Symptoms are easier to detect, but when we can detect the root causes, we are trying to do it. But generally, it's very difficult to follow the root cause.
Yes, that's totally true. Thank you, Rached. Very interesting work.
Thank you. Thank you.
Thank you, Diego. Any more questions for Rached? Ahmad, please go ahead.
Yes, first of all, thank you, Rached, for the interesting and nice presentation. Actually, I have two questions for you. So the first question, which is related to the evaluation of the debugger. I'm wondering if you consider to evaluate the cost of running the debugger, right? So because what I understood, it will be somehow a comprehensive debugger covering many issues, many things, right? But do you think, or are you planning, let me say, okay, for example, to evaluate the performance in terms of time and resources, does it need to run this debugger, right? This is my first question. I'm not sure if you want to answer it before moving to the next question.
Yeah, I answered the first. So for the time, that's true. It's very important aspect we have to evaluate. And of course, now during the training, we focus a lot on the time that and the cost of doing this debuggers. We are trying always to compare between without the debugger and with the debugger, how much time it will add. For now, it's okay. It's still okay. We didn't add a lot of time, so we're still happy with the performance we have. And also in like the version we will produce for the framework, we will be doing it in parallel. It will run in a separate thread. It won't like run during the training. It will be in parallel. That's what it means. So it won't cost anything.
Cool. Yeah, thank you. And my next question, actually, I'm not sure if it missed me or not. Could you at least give me an insight about the checks related to the selection of the wrong activation function in the debugger?
Okay. So for the wrong activation, I don't think we have yet started like evaluating that part. But I think that we have some. Yeah, we still haven't yet started that part.
No, it is.
But like we are following some researches done in like traditional neural networks. We're trying to apply those. But you know, I don't want to give you like incomplete information about that. So once we finish it, we will. It will be published in the preprint.
Yeah, no worries. Yeah, again, it's a very nice project, and wish you best of luck continuing working on it. Thank you.
Thank you, Ahmed. Pierre-Olivier, please go ahead with your question.
All right. Hi, Rached. Thank you for the talk. I was looking forward to it. So my first question is, you mentioned maybe with the debugger, you will be able to detect bad exploration. How can you detect bad exploration of an agent? How can you know that with more exploration, you would have better performance?
So for now, we are trying to solve that from the point of view of the algorithm used for the exploration. As I said, for example, the epsilon greedy, for example, we can look at different parameters, how the epsilon was initialized and so on. So we have defined some rules. Like I can give you an example. People, when they initialize the epsilon, sometimes they make mistakes. They initialize from 0 or from 1 instead of 0, while it should be initialized from 0, because it will start from 0 and then keeps on increasing until reaching 1. So we are doing this kind of checks. Right now, it's still algorithm-wise, if I can say. We are looking at each algorithm, exploration algorithm, but we're starting to looking at some metrics they use to evaluate the exploration coverage. So we are trying to introduce some exploration coverage as a metric to evaluate how good was the exploration.
Okay, interesting. And my other question is on if you can go back to slide 11.
Slide 11. Yeah,
there. You mentioned that, right there, you write reproduce the bug. How do you reproduce the bug? I guess you took it from Stack Overflow. Yeah. How are you able to reproduce the bug because on Stack Overflow you don't always have like the full code that lead to the problem.
That's true.
Yeah.
That's
how are you able?
That's the problem. It's not easy like to reproduce the bug. Most of the cases we try to use the ones that were they come with the code. We try to use them to reproduce the bug, but in many cases we don't really have the code, but we can use the explanation they provide in their post. reproduce the code. And of course, we have some in the project. We have some people, domain experts in reinforcement learning, so they can like validate if we have simulated the bug correctly.
Okay, really interesting. Thank you, Rached.
Thank you.
Thank you, Pierre-Olivier. And thank you to everyone for your questions. If there are no further questions for Rached, I see we're pretty much out of time for our webinar today. So I'd like to once again thank our speakers, Ernesto and Rached, for sharing their research topics with us. This was a really excellent Trainee Talks session and a great way to end the fall semester. And thank you too to everyone who joined us today. Stay tuned for the next edition of Trainee Talks coming to you in the new year. Happy holidays, everybody.
Thank you.
Thank you. Happy holidays.
Happy holidays.
Happy holiday. Thank you.
Thanks. Bye-bye.
Thank you.